Hi, this is our second video in dimensionality reduction for data visualization. In the previous one, we talked about PCA, principal component analysis, but in this one, we will talk about an algorithm that is called tsne. It stands for T distributed, the T is for T-student distribution, the S is for stochastic neighbor embedding. So what is tsne? What is T distributed stochastic neighbor embedding? So it's a non-linear dimensionality reduction technique. Remember that PCA is linear. Well, this one it's for non-linear relationships. It means that we will be able to capture more complex relationships among our variables. Now, tsne it's mainly used for visualization, so it's not really used for modeling because PCA can be used for both. You can use it just to visualize data, but also when you are modeling. And by modeling, the idea that I want to say here is like imagine a problem where we have multiple variables initially, let's say x1, x2, up to xk. Xk can be like 100 variables or even more than that, right? So that's our original problem. But then we find components. So I'm gonna the principal components. This is for PCA. So we have C1, C2 up to CK, right? And then we try to take a subset of the principal components, which represent most of the variance, right, in our data. So typically they will capture like between 85 to 95% of the variance of the data. So with this subset of components, we create the model. So let's say that you wanna predict a numerical variable, so that would be a regression, or if it's a classification, then you use the subset of components. So this is for modeling. So PCA is useful for this, so to simplify the original problem into some components and then to create the model. tsne is not used for that typically. The main use is for visualization purposes. So we use it when we want to see our data in 2 dimensions or 3 dimensions. So in a problem where you have more than 10 variables and you want to be able to visualize those numerical variables in a single plot. So that's when you use this technique. It was created in 2008. So maybe you're thinking, oh, that it's old, but it's not. I mean, 70 years old, it's not a big deal. I mean, if you consider that regression model was created like almost 150 years ago, that's a lot of time, right? So 17 years, it's fairly new. Okay, so with tsne, we will be able to capture complex nonlinear relationships. Now, what are the benefits with PCA? In general, tsne is designed to preserve the local structure. That means that points that are together are going to remain together. So it's very useful for clustering. So if you want to see like different, like how your data is clustered, how many groups you have. So it's a great idea to use this technique because it's going to preserve the local structure. That means that points that are similar are going to try to keep in a lower space also close to each other. And those points that are like different, they are going to be far from each other. So in the case of PCA, PCA does not care that much about the local structure. It cares more about the global structure. So it tries to like maximize the variance that is explained. Now, what are the steps of this algorithm? So first, we compute the similarities between points in the original space. So this is important because with these similarities, we know which points are similar, right? Which are close to each other and which on the contrary are different. So with these metrics, with the similarity, we will be able to put them together. So once we know the similarity matrix, then we map the points in a lower dimensional space because that's the whole purpose of tsne to perform a dimensionality reduction. And once we have lowered the dimension of our original problem, then we optimized the mapping, trying to ensure that we put together points that are similar. That's the idea. Remember that tsne has a n, that's for neighbors. In machine learning, this is a very common algorithm to include the neighbors in the area. I'm pretty sure that some of you have heard of KNN, K nearest neighbors, KNN. KNN is used for regression and even for classification purposes. These ideas are inspired by some of the phrases that maybe you have heard from your parents, like you are who you surround yourself with, or like birds of a feather flock together. Is that it's the same idea of KNN? So let me show you real quick how KNN works, which is a different algorithm, but again it uses the idea of neighbors. Let's say that we wanna classify transactions if they are like fraud or like like suspicious transactions. So we have the X for those transactions, and then we also have the like good transactions in our data set. So these are the checks here, good transactions, right? Then in this algorithm, I'm going to use a k equal to 3. You can test different values, 3, 4, 5. All right, so there is a new point, a new observation. Let's say that I have that observation here in this part. This is my new observation, the dot that is here. And I want to classify that transaction to see whether it is a suspicious, like fraud, or if it's an okay normal transaction. So k equal to 3 means that for this point, we want to find where are the 3 closest points. It's not perfect. I'm going to try to, let's assume that these are the 3 closest points, right? So the KNN works just like, okay, if I want to classify the new observation, so let's just vote with the K neighbors. So the 3 neighbors here, there are two bad transactions or fraud, and there is 1 transaction that is okay. So the majority here, it's an X, right? Therefore, this point is going to be predicted as an X. So it's a bad transaction. So using the neighbors, we're predicting the behavior of this. So same here, the same idea here. We want to keep together points that are similar to each other. Okay, so in this example, here there are 2 plots. This is the original 2-dimension space. We have X and Y, or X1 and X2, right? And here you can see there are 3 groups. So in the dimensionality reduction, we want to go to a single dimension, which is going to be the line, right? And the idea is that we keep the initial structure. That means that the points that are similar, they're going to be clustered together. And that's what's happening here, right? That's the idea. This is what we want, right? To lower the dimension of our problem, but at the same time ensure that we will keep together the groups or the clusters. That's why we use this technique mainly for to visualize a clustering problem or even a classification problem. So let me show you the challenges. In this problem, we have the 3 groups again, but if we try to like shift everything to a single dimension to this vertical line, so the orange group is fine, this group here is fine, right? But these two, if you just project the points here in the line, they will overlap, right? And then you won't keep the difference that was in the original data set. Same idea here in the second plot. We have our 3 groups, but now if we try to project these observations in the x-axis in a single dimension, so this group is going to be fine, but now we're overlapping these two. So it will be a mess, right, if we try to analyze them. So the idea of tsne is that, okay, it's going to project or it's going to lower the dimension of our observations, but then it starts moving the observations to ensure that those observations that are equal to each other, they remain close in the same group or in the same cluster. And some idea goes like if it's going to try to keep them apart if they are different. That's why the first step is to compute the similarity. So for example, here we have the orange points. So then it's going to start moving them to ensure that this one, for example, is going to join them. Same thing with this one. So that's why tsne takes time. It's not from the computing perspective, it requires more resources compared to the PCA. So this is a quick comparison between tsne and PCA. So tsne works for nonlinear relationships, while PCA is mainly for linear. tsne preserves local structure, the groups, right? It tries to maintain the original groups, while PCA does not care that much about local groups. It cares more about the global variance to capture the variance in the original data. From the computation perspective, tsne is more expensive. It requires more resources, while PCA is faster because it's linear. Remember that in data science and even optimization, if your model is linear, it means that it's easy to solve. If it's non-linear, then it's more complex. The solution is you're not going to have like a closed solution, and it will take more time. So the usage is also that there are differences here because tsne is mainly for visualization purposes, while PCA is a little bit more flexible because it works for visualization, but it also works for modeling. Okay, so let's go to the example. We will use the same cancer problem that we were solving in the PCA session. So the libraries here, again, we're using scikit-learn, PCA, and we're adding here tsne, right? Which is the new algorithm. So let's compare PCA and tsne in the same data set. So let's solve two problems. So the first step for PCA and also for tsne, remember that we standardize or normalize our data. So initially we had here 30 observations, right? And we scale them. We transform our observation, we standardize them. So now the mean for each variable is equal to 0, and the variance and the standard deviation both are equal to 1. That's for every single variable here. So once we have normalized the data, so we're creating two principal components. We did this in our previous session, and then we visualize the components. With the two components, we visualize our data set, right? So here we're summarizing 30 variables in 2 dimensions. With PCA, yeah, remember that we were able to see that the groups, the two groups, the two tumors are separable, they can be classified, right? Now let's do the same with tsne. So it looks a little bit similar. So we call the algorithm of tsne how many dimensions we want. There are some hyperparameters here, like the perplexity. Perplexity typically will go from 5 to 50, and a lower number, a lower perplexity means that you're going to prioritize the local structure, like like the group's going to be closer together, while higher numbers, like close to 50 or more, means that you're going to prioritize more like the global structure. So in general, remember the difference between a parameter and a hyperparameter. Parameters are estimated when you train your model. For example, in a linear regression model, remember the equation is y equal to beta 0 plus beta 1x1 plus beta 3x3. So those betas are coefficients because when we provide the historical data to our analysis, when you train the algorithm, well, it's going to estimate the betas using that original table, right? The historical data. So that's a parameter. Now, a hyperparameter, it has to be given from the beginning, like even before training the model. So it's not estimated using your data. You have to provide a value for the hyperparameter before. That's why in machine learning, we talk about hyperparameter tuning. That means that we test different values for the hyperparameters to find like which are the values that will provide you the best fit, right? The best performance. So that's the difference between a parameter and a hyperparameter. The parameters are estimated with the data when you're training your model, while the hyperparameters, they are required to be provided before. An example of hyperparameter in clustering, for example, in k-means, the k, the number of groups or clusters that you want to find, that's a hyperparameter because you define the number before running the algorithm, right? That's an example. Same thing if you're doing regression or classification with a tree, with a regression or classification tree, you need to provide the max depth, right? So like the maximum number of ramifications that you will, number of levels of your tree. So that's a hyperparameter because it's defined before. All right. So we train, we transform our data, our normalized data with tsne. So this is the transform data using the new algorithm. And now we get the plot. Maybe in this example, you won't see big differences. The only difference, if you notice, because in both cases, PCA and tsne are doing a good job for this specific problem. So maybe what you will notice is like tsne is trying to like separate a little bit more the classes. So this is PCA. So please notice that the blue dots, most of them are close to the border. But in tsne, if you notice, most of them are going like are going to be like are more separated than the other class. Like the zeros here are more separated than the ones. Even though there are some specific points that are like overlapping, but most of them are more separated compared to this plot. But again, in this example, the difference is not that big because that's normal. In machine learning, it's difficult to generalize that an algorithm is going to be the best in every single data set that you use. So same thing here with the dimensionality reduction techniques. So let's go to a second example. This data set comes from scikit-learn. It's about digits. So there are some like images of digits, numbers from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's why, that's the target. It's a classification problem. You want to classify the digit. And the variable, the x variables here are pixels because we have images. So these images are 8 times 8. So that means that there are 64 variables, right? 64 pixels. These are the variables, the pixels, and the value for each pixel. So we know the x variables are 64 pixels, and the y variable or the label is the digit, the value. Like if it's the number 0, 1, 2, 3, 4, 5, up to 8. All right. So this is a classification problem, and we're going to use both techniques, PCA and tsne, with the idea to visualize if we can like classify the values, if it's possible to separate them before we create our models. This is again, I'm using this for the EDA, for the exploration part. Okay, so we transform our data, we normalize the data, remember? This is when we find Z. So now each variable or each pixel has a mean equal to 0 and a standard deviation equal to 1. So we apply the PCA, same code that we use in our previous video, and we plot the 10 classes, numbers from 0 to 9. So even though you can see the groups or the digits, the observations, there is overlap, especially here in the middle of the plot. There is a mess here, right, in this part. This is for PCA. Now, using the same data, let's perform tsne. Same steps that we used before in example number 1. But now, please notice that tsne, which is not a surprise, it's doing a better job maintaining the local structures, representing the local structures. So the groups are well defined, are better defined here. The overlapping is not that big compared to PCA in this specific problem. So that's why this technique is useful, because when there are no linearities, a high complexity, here we have 9 classes. There are 10 classes because from 0 to 9. So the complexity is higher. tsne is doing a better job compared to PCA here. We can see clearly that it will be possible to classify these digits because we can see that now. Now, the beauty of this technique is like we're representing here like 64 variables. And how can you do that, right? It's difficult to bring 64 variables and translate that into only two variables, right? So that's when you use the dimensionality reduction techniques. Okay, so what are the advantages of this algorithm? Well, the first one is that it preserves the local structures well, and we were able to see that in the second example. It's very useful for clustering and also classification as the problem that we provided. So it's effective for high dimensional visualization, not for modeling, right? So the limitations is that it's completely expensive, it takes time. It's sensitive to hyperparameters, especially the perplexity. You need to like change that value. There are different ways to evaluate that. There is like a grid search where you explore all the possibilities. Another limitation is that it does not present well the global structure because it prioritizes the local structure. So what are the main insights here? So tsne is a powerful visualization for visualization. It's really useful, especially when you have non-linear relationships and your data set is complex. Typically, it's used for the EDA, right? For visualization purposes and not for modeling, right? That's like it's important to have that distinction. PCA, on the contrary, it's a little bit more flexible. It can be used for both. All right, I'm gonna finish the video for now. I'll see you in the next lecture.